Testing. Cool. Good morning, everyone. Welcome to our second day of the Small Satellite Education Conference. Thank you again for attending here, and we hope you had a good first day. Some very quick morning announcements for you guys. Today, we have several speeches in the early morning before we do a break, and then one of our big activities towards, I'm going to say around the 10:45 time frame, is a legislative panel with Representative Thad Altman, as they're going to sit up here and take some questions from our moderator. Later, after that, we're going to wrap up with some additional speeches going about the various sites, some Ph.D.s, as well as AMF is going to have a speaker talking about everything that they're doing up here. One other thing that we would like to note is that right now it's looking like our closing time is around 12:30, 1:30. So afterwards, you do have free reign to take a look and tour the Space Center Visitors Complex. So please, if you get a chance, look around everything, see what you can do. There is a lot to do here. And please, once again, as we go throughout the conference, you're going to see the QR code behind us. Leave us feedback. Let us know what we can improve for the next time. Let us know what we're doing well so that we can reinforce it. But with that said, I'm going to turn it over to Kevin and go ahead and take us away.
Thanks, Kevin. So our first presenters today, I first met, they were probably in the 4th grade. Looking forward to being a part of this new aerospace team I was starting at a middle school. They really got involved starting in the 5th grade, but now they're high school juniors, and they really have an impressive body of work to share with you. So today our first presentation from William Mayville and Theo Ouyang is about the Wolf-C program and the FlipSat space mission. So let me welcome William and Theo to the stage.
Good morning. It's really great to see you all here at the first annual SmallSat Education Conference. I'm William Mayville. This is my colleague, Theo Ouyang. So let's begin. So let's first begin by discussing the current STEM education model, or more specifically, why it's ineffective. We see that the current model falls short for a number of reasons. First, we see that the current STEM education, at least in the United States, does not develop critical 21st century skills like innovation, critical thinking, and so forth. These skills are critical in the private sector, and by not effectively educating students about them, we are preparing students to fail in the STEM workforce. But even on the technical side, we see that STEM education is detached from industry because it is conceptual and it's siloed, with students simply memorizing information for the next test as opposed to actually understanding the content and applying it in a number of practical manners. The impact of this is that there is workforce depletion. We see that there is an excess of demand for labor in STEM fields such as aerospace, with a recent US Census Bureau study indicating that only 28% of STEM-educated students actually enter STEM careers. This is not merely a short-term solution, a short-term problem that will come to pass in a few years. Rather, it is a long-term problem that requires a long-term solution. And the long-term solution that will effectively solve this problem is the implementation of experimental learning and hands-on educational experiences in STEM at the secondary level of education. Of course, I'm referring to middle and high schools. The WCDT and Wolf-C have solved this problem to an extent. However, that's something I'm going to address a bit later in the presentation. We see that one of the solutions to this problem is provided by the CubeSat and similar technologies. CubeSat has already been demonstrated to be highly effective educational tools for STEM education, as can be seen through their usage at the university level and through the number of presentations that we had yesterday about nanosatellites and CubeSats being utilized by university teams and students. The reason why CubeSats are so effective in this regard is because, as far as aerospace goes, they're relatively simple, relatively inexpensive, but still provide real-world experience using actual payloads that can yield actual scientific results that can also be used for data analysis studies and so forth. The problem is, while CubeSats are considerably more accessible than some of the past larger satellites that could only be accessed by major companies or governments, is that while CubeSats are accessible by universities, yes, for middle and high schools, secondary education in general, funding is still a major problem because CubeSats are still fairly expensive. In addition, we see that the lack of curriculum development for CubeSats and other hands-on aerospace technologies in STEM at the secondary level of education are lacking. And as a result, and as part of this, we see that there are very little instructors that are effectively trained in the utilization of hands-on technologies such as CubeSats at the secondary level. And all these factors, when taken in aggregate, significantly harm the accessibility of CubeSats and other such technologies at the secondary level. As stated previously, this problem has been solved to an extent by the WCDT as well as WolfC. However, I'm going to get to that a bit later in the presentation because first I'd like to address a NASA-sponsored solution called the CubeSat Launch Initiative, or CSLI. The CSLI is a great program for universities and other such institutions. However, that is also the problem because while it is an effective funding method, it is focused on research institutions, universities, and other such entities, as opposed to middle and high school teams. So this leads to really a trifecta of problems. First, you have middle and high school students competing against undergraduate and graduate students, as well as postdoctoral researchers. Obviously, this disparity leads to a disparity in the quality of the proposed missions, and as such, missions that are considerably of high quality for middle and high school students are simply overshadowed by proposals from higher education. As such, viable missions from the secondary level are simply bypassed in favor of other missions from colleges and other such institutions. Second, these students, whether they be secondary students or students in higher education, are competing for a very small amount of slots, usually ranging from 10 to 20. This further intensifies competition. Third, NASA prioritizes proposed missions that meet NASA's mission objectives and goals. Of course, this is their prerogative to do so, and I take no issue with this. We see that the fact that these mission objectives are usually vaguely worded, or at the very least slightly unclear, means that secondary students are further disenfranchised. Ultimately, this shows that a change is necessary to a system that is favorable towards secondary students in order to extend the STEM pipeline to that level in an effective manner. This is where I'd like to introduce the WISat-1. The WISat-1 was the first CubeSat to be designed, built, tested, and flown with middle school students. And it was created really in 6 stages. First, selection, development, testing and integration, launch, and operations. Each one of these steps was hands-on and real-world, enabled students to develop communication skills, collaboration skills, innovation skills, and other such 21st century skills that are essential to success in the private sector. Furthermore, it also enabled students to develop a number of technical skills and other such hard skills that are equally as essential for success in STEM. The WISat-1 model is something that we wish to replicate, not just with our own programs with the WCDT, but also at other schools and such institutions across the country, and hopefully in the long term across the world. With that, I'd like to introduce the CubeSat-1. The CubeSat-1 is a program a mission that was launched in July, and it is looking into the viability of capacitors as an alternative to LiPo batteries. Ultimately, the CubeSat-1 is further evidence that middle school students are capable of engaging in real-world aerospace activities when given the necessary opportunities. Now I'd like to introduce the FlipSat-1. The FlipSat-1 is a hosted payload mission, which my colleague Theo will speak more about later in the presentation. So I'm just going to do a quick summary. It's just looking at a number of methods it's just looking at the viability of a number of methods of radiation hardening in order to accomplish efficiency, and both in terms of cost as well as functionality. Of course, Theo will expound more on that later in the presentation. The FlipSat-1 is also a proof of concept mission for WolfC, and I'll get into that later. The solution that is being pioneered currently by WolfC and the WCDT is hands-on learning, and the goal of this is the development of smart creatives. This means students are not just adept in hard skills, but also in soft skills as well. And this is really focusing on the STEM pipeline in order to effectively develop students not just to succeed on the next test or assessment, but rather to succeed in the workforce in the private sector and make valuable contributions to society as well as the field they're in. This leads to the first of two goals of WolfC. The first goal is a short-term goal, and that is the funding of viable programs/projects, and whether that be through a grant system or through the manner in which we're funding FlipSat 1, or if you were here yesterday, some of our international initiatives that I discussed, such as our work with One Voice for Change, funding students in Peru to receive A3CubeSat emulators. The goal of this phase is to provide students with access to the technology and experiences they need in order to really effectively be prepared to fully participate in the STEM workforce down the road. The second part of the solution is more of a long-term solution, and this is changing the way STEM education happens, generally speaking. And specifically, we're going to be looking at STEM instructors. This is a multi-step process, and we're going to begin by identifying knowledgeable instructors through methods such as social networking platforms, as well as through conferences such as this one. And once we identify those knowledgeable instructors, we're going to see which of those instructors are motivated to affect change in STEM education. And we're going to then partner with those educators. There are several desired outcomes of this. The first is the creation of educational seminars and conferences such as this one that bring the private sector and academia together in order to discuss how STEM education could be furthered utilizing nanosatellites and other such technologies. As part of this, there will be the creation of CubeSat curriculum in order to help prepare teachers engage in CubeSat-based lessons, activities, and programs and projects in an organized manner that is helpful to students. And as part of this, the end goal is independent program growth of grassroots programs that aren't necessarily directly affiliated with WolfC or the WCDT. And this is what we will consider to be success in this regard. This is where I'd like to introduce the FlipSat 1. The FlipSat 1 is the proof of concept program for WolfC. We've already worked with a number of private sector entities to raise the funds for the integration, testing, and launch of the FlipSat 1. And we see that this demonstrates that the first component of the plan, which I discussed earlier, is viable. When we look at the educational component, we've already demonstrated student interest and student ability, with the FlipSat 1 team becoming one of the largest on-campus student organizations in a matter of months. In addition, the FlipSat 1 team has made a number of technical strides, which I'll allow Theo to discuss in further depth in a few minutes, further demonstrating student ability. Ultimately, the FlipSat 1 demonstrates the viability of WolfC, not just as a funding mechanism, but also as a method to further STEM education at the secondary level.
Thank you, William. Hello and good morning. As William said, I'm Theo Ouyang. I'm the principal investigator for the FlipSat 1. So the mission statement of the FlipSat 1 is providing space-related experience to students while researching the volatility of single-event upsets within circuit boards with respect to radiation methods. Basically, we're testing 3 different methods of radiation protection to prevent single-event upsets. We're testing watchdog timers, radiation hardening, and error correcting code. To do this, we're using microbits as our onboard computer to provide spaceflight heritage for the educational platform while using microprocessors that I don't have the name here, as our testing units. So as I said, we're using microbits as the onboard computer for the FlipSat 1. We're doing this to provide spaceflight heritage to the educational platform. These were originally developed by the British Broadcasting Corporation as an educational tool for students in the UK, but now we're trying to show greater capability to them. On our testing units, the microprocessors will have octet sequences of bytes, and we'll have varying radiation protection amounts and types on each of these microprocessors. Through this, we can show a causation effect through the different types of radiation protection and how much protection they actually provide. And then for each of these different types and amounts of radiation protection, we will have varying circuit board counts in order to achieve statistical significance according to a student's t-test. So for our first method of radiation protection, we're using physical protection. We've chosen polyethylene for our physical protection, as polyethylene has a very high hydrogen count. Hydrogen is a really good radiation protectant. It's another reason why water is really good for stopping radiation. And that's why polyethylene is already a prevalent method of radiation protection here on Earth. So our microprocessors will be fully encapsulated beyond axis and structural holes, so our power, ground, and data pins, and then mounts to connect it to our chassis. And then our thicknesses will range from 5 to 10 millimeters. However, last week during testing, we found that this would be too thick for outgassing and also volume volume requirements, so we're changing that to 1 to 5 millimeters, and due to the scope and duration of the mission, we'll be able to achieve causation and statistical significance just through the pure time. And then for each of these thickness ranges that we've chosen in 1 millimeter increments, so 1, 2, 3, 4, and 5, we'll have 2 printed circuit boards assigned to it so that we can have some redundancy in case one of them fails. Our second method of radiation protection that we're testing are error correcting codes. Is error correcting code. We're using parity checks since they're really basic. It's basically you take a byte, first 7 bits or last 7 bits, you sum them up. That summation is a number, and all numbers are either even or odd, and that's called a parity. And that parity is then assigned to the parity bit. So that summation is even, then your parity bit is going to be a 0, which is even. And that summation is odd, then your parity bit is going to be 1, which is odd. Through this, if there's an odd amount of single band offsets, so 1, the most likely case, 3, 5, etc., if that occurs, then the parity bit and the parity summation no longer match up. You have even or odd and even, and there you've known that an error has occurred. From there, we use forward error correction. So all of the octet series or bytes that we're going to be using are going to be repetitive, meaning that we're going to have a library of known bytes that we're going to be utilizing throughout. Through this, we can compare our errored bytes with the library of known correct bytes and basically auto-correct it to whatever is closest, and then rewrite it. Our final method of radiation protection that we're testing are washout timers. Here we're efficiency testing them because they have basically 100%, they work fully because they just reset the system. And we're using electronic and physical washout timers as our methods of testing. Washout timers are already prevalent methods of protection against single event upsets. And the way they work is that the microprocessors send a kick to the washout timer every interval or just based on a cue. And if it doesn't send that kick, then the washout timer will reset the microcontroller. So for the electronic washout timers, we'll have a program running for the internal central processor of the SmallSat 1. This is the microbit that I talked about earlier. And then the amount of electricity usage by this code will be measured. And then through this, we can compare the amount of single band offsets fixed by measuring the data stored before and after to calculate how many single band offsets have been fixed, and then comparing this with that electricity usage. From this, we get a cost worth value. Our second method of watchdog timer testing that we'll be utilizing are physical watchdog timers. Here, the kicks will be registered and executed physically. We'll use a physical timer for setting off our resets. However, we will have as little electronic involvement as possible, but the actual reset of the system will be electronic, since it's an electronic system. And then once again, the amount of single band offsets that we have fixed will be weighed against the weight and electricity cost of the physical watchdog timers. The impact that we hope to have with the SmallSat 1 is we hope to have an increased cost effectiveness of radiation protection in satellites. We hope to have an increased understanding of radiation and the methods of protection against it, specifically for small satellites such as our own, and we hope to be a stepping stone for further radiation research, either by us, other educational institutions, or other organizations. Finally, we hope to have educational benefit, either directly through the experience of the students on our team or through outreach that we do. We also hope to be a successful proof of concept mission for the Wolf Sea program.
Thank you. And once again, we are very excited to be working with the SmallSat 1 program at Wolf Sea. So just a quick summary of the goals of Wolf Sea that I've discussed throughout this presentation. Our first goal is to diversify the CubeSat funding pool in a number of methods, whether that be the funding of projects such as Theo's, a system in order to systematically provide grants to eligible schools and teams with viable proposals, or international initiatives such as the initiative we're working on with One Voice for Change, involving the 15 student teams in Peru. Our second goal is to change the way STEM education occurs on a fundamental manner. And we plan to do this through expanding the network of knowledgeable and motivated instructors, as well as through the creation of educational seminars. And the goal of this is to create CubeSat curricula, as well as to really foster independent program growth throughout the country and hopefully, eventually, throughout the world. The new space economy that we are currently living in presents a number of opportunities that are completely unprecedented. However, in order to really take advantage of those opportunities to the greatest extent, it's imperative that we have an effective STEM pipeline that prepares students for success in the STEM workforce. As such, a fundamental shift is necessary to experiential hands in order to effectively accomplish this task, and we're currently seeking out donors, sponsors, and partners who are willing to work with us on such initiatives. Ultimately, the message I want you to take away from this is that when given the right opportunities, Students are not just able to enter STEM, they are able to thrive in STEM. Thank you, and I hope you enjoy the conference.
Next up, we're privileged. It's really a great thing. We have Dr. Kang, who has agreed to share a little bit more about the Naval Academy today. So if Jen, if you're ready, we'll bring you up. We have a couple more presentations, and then we're going to again take a break. Following the break, we're going to have our round table. And again, welcome. Thank you for being here.
Thank you. I would like to tell you a little bit about our satellite program at the Naval Academy. So I'll describe the curriculum a little bit. It may be different from sort of typical university curriculum. So I'll talk about that, and I'm going to flash through a whole lot of pictures really fast about showing you some of the pictures of the satellites that we've launched in the past. And then I want to spend a little bit of time on the lessons learned. I have some interesting stories to tell you, and I think it may benefit to some of you who are developing your satellites. So our aerospace engineering curriculum, it's a one major, so it's aerospace engineering major. And at the Naval Academy, all the freshmen, they all go through the same curriculum. So they don't decide their major during their freshman year. It's sophomore year when they start their majors. So sophomore year, what we do is we have all our incoming aerospace engineering students. We give them the Intro to Aeronautics and Intro to Astronautics courses that everyone takes, and then they decide which track they want to go into. So starting junior year, the track splits off. So you could either go aeronautics, which is air-breathing aircraft, rotary wing type stuff, and then astronautics, which is satellites and rockets. Ours, Naval Academy is the undergraduate-only institution. What that means is basically great opportunity for the students. So if you kind of imagine a university or colleges with all kinds of equipment, facilities, research projects going on, they're sometimes focused on the graduate students, Ph.D. students, and professors. Here at the Academy, everything you see around the campus is all for the students. So it's a great opportunity for the undergrads to be playing around with these expensive equipment, and it's all dedicated for them. So I think that's one of the attractions for our Naval Academy. So some take, and as you can see, they're very heavily focused on rockets. So a little bit of introduction to our satellite program. So what we call that Naval Academy Small Satellite Program. And of course, the main focus is to train and educate our students in the arts of satellite and space development technology. We're very lucky in that we have all the equipment and facility to be able to support up to 3 U-size CubeSats all in-house, so we don't have to depend on any of the external entities, and I'm very grateful for that. Some of the equipments include a vibration table for vibration tests, thermal vacuum chambers, solar simulators, all of those things. So we have very good facilities. 2001, and since then we put about 16 space payloads in orbit, and I'll show you pictures of some of those. So this was a very first satellite that launched. It was launched in 2001. It's the longest, as far as I know, it's the longest surviving student-built satellite on orbit right now. And when I say surviving, one of the solar panels still kind of works. So if the sunlight hits it just right, it comes alive for about 20 minutes out of a month, and then still beeps once in a while. So that's on orbit still and somewhat operating. In 2012, we switched from the microsatellite, the little bigger one that you just saw, to a CubeSats. We did this so that we could accelerate the development cycle. We want the students to build the students while students are still students. So we want them to go through a fast cycle and see the entire development cycle from the concept all the way to launch and operation. So we switched to CubeSat, and this was the first one that launched. And then we started using 1.5U, so we have a little more room. And what we like to do is we usually launch 2 satellites together. So when they're 1.5U, we get to occupy the entire 3U pod, and we get to do whatever we want with that without having to coordinate with other people. So most of our satellites that we've launched since are 1.5U, and here's an example of a communication satellite. Once in a while, we get good funding and some leadership so that we get to launch some fancy satellites. So here's an example of the fanciest one that we launched. Full 3U, it had the attitude control, all kinds of high-tech stuff, deployable solar panels. So that was kind of exciting for us to be able to play with some expensive satellites there. Here's an example of partnerships with other research entities. So this one was the George Washington University developed thrusters. So if you look at the cut up opening, you see little 4 separated circles, aluminum things. Those are micro cathode thrusters. So electric propulsion we were testing out in space. So that was an example of that. And here's a follow-on mission for the communication. I'm sorry, there's a follow-on mission for that electric propulsion test that we did, and some more communication satellites that we've been launching. Sort of different flavor that we have been trying in the past few years is on-orbit servicing side of things. So we still wanted to keep everything in the CubeSat scale and wanted to do different things. So it's sort of a vision. We won't get there for a few years, but having a sort of tug satellite with propulsion unit delivering these robotic arm satellites somewhere, and then it could do some simple diagnostics and things like that. And then a quick shout out to the University NanoSat program, which you heard about yesterday. This was an entry to that, I think 3-4 years ago. Phenomenal program, so I encourage everyone to look into that. Here's a picture of the robotic arm satellite folded up, ready to go. So this was actually launched in 2018 as a free flyer to test out the arm movement. Unfortunately, that one was dead on arrival, so we didn't get any data back. So we don't know how well the arms worked. So for next iteration, we decided to just put that inside the International Space Station. That way, the communication and power is pretty much guaranteed, so we don't have to worry about that. And if anything goes wrong, it's the arm, so we could get more data off of that. So this is the International Space Station version of it. We're going to get them mounted on the inside of the station. Pictures on the left show the targets that the arms will be manipulating, doing a little bit of handoffs, things like that. A picture in the middle shows the 3D camera mounted in the middle of the structure, and picture on the right is an example of the electronics that go in controlling the motors. We did a final fit check out at the NASA Marshall, and we're going to be installed in a box just like that. So this is a mock-up, ground mock-up of where it's going to get installed. A picture in the middle is shows our final satellite model being what it will look like inside the MSG is called, that it's going to be installed inside. So this one is going up next week, next Sunday, out of NASA Wallops. So we're very excited. I'm super nervous. My students are excited. We'll see how well that goes. So those are some of the examples of the projects that we're working on. And what I really wanted to spend a little bit of time on is share with you some of the lessons learned, the scars and bruises that I got. I thought it would be good to share with the community. So documentation, we all know that it's very important. Us engineers really just like to play with our toys, and we are very resistant to documenting. With students, it's like pulling teeth. And basically, I've given up on trying to motivate students to document. So now I just force students to do the documentation. The good news about that is by the time they graduate, they hear from NASA that certain documents are needed, and they kind of think back, oh yeah, that's the documentation this guy was talking about. So they learn their lesson. So at the end of the day, mission achieved. I haven't yet found a good way to make that sort of self-driven, motivational. So for now, I'm just making my students do it. But they do learn, and they do see the importance by the time they graduate. So I guess that's a win. I tell my students to take pictures of everything, especially when documentation is lacking. It's a big deal. It may end up saving your life. I'll give you a quick example. That little circle you see there, inside there, it's hard to see, but there's an SD card for our main processor. The way our satellites go is we stack them up. So the SD card board is all the way on the bottom, and then we stack up our boards, put the structure on top, integrate solar panels, and then it's ready to go. So we go through a couple of days integrating all of this stuff, and then we have a fully built satellite sitting on our table, so we're taking good pictures of it because it's so pretty. And then we realize there's a SD card sitting next to the satellite. Now, did we forget to put that in, or is it just a spare hanging out? No documentation to support one way or the other. Normal way would have been to disassemble everything, go through the whole procedure, and waste about a week doing it. We went through our pictures and found this picture, and you could kind of see the SD card stuck in there. So they saved us about 1 week of aggravation and tears. So again, pictures are very important. Highly encourage you to do that. We all know that the technology is advancing and everything's shrinking, which is great. When we're dealing with CubeSats, we are limited in volume and mass, so electronics getting smaller is a good thing. Big plate you see on the upper left, that's about 2 foot by foot. Now that all of that fits into a single little board, and now we fly that on all our CubeSats. It's a communication board. That's good, but I'm a little bit resistant to components that have too small parts, too small of components on them. I like my electronic boards to have finger-friendly parts. It's a student-built satellite. I'm gonna have them solder on the parts themselves. It's easier to troubleshoot. It's easier for them to assemble instead of having the very high-tech cell phone-looking electronic pieces. I really like having bigger components like that. That students quickly learn how to assemble and make adjustments to it. They just never stop trying to improve it. So you get this abomination as shown in the picture here. It is also important for the students to learn when good enough is good enough and then be able to move on. Another advantage of having big components is that your satellite's light. What that means is you can always put ballast to get it to the exact mass that you want. So in this case, in this example, we put the full ballast under to make it full mass and so that it stays up on orbit longer. I don't know if you heard about this, but the requirements for your satellites deorbiting is getting reduced from 25 years down to 5 years. Now, whatever you put up there needs to deorbit within 5 years. So this plays into that in that when you have these big component parts, you're less dense and it's easier for you to deorbit faster. So again, having big component hand-friendly, finger-friendly components may actually help you in upcoming years. What you see there is a full flight-ready component that was to be delivered in a few days, and that's completely fried. So schools, low budgets, right? Beg, borrow, steal is what we operate on. In this case, one of the engineers picked up a oven from one of the used parts store and thought it would be a good idea to use that to do our bake-out. Did a little bit of testing, seemed to be working, so they left it in the oven they found for, what was it, like $12 or whatever. I left it overnight, came back and saw this. So sometimes it's worth, especially when you're dealing with flight hardware, it's definitely worth going to the extra little bit, spending the money and getting it right so that you don't do this to your flight hardware like 3 days before you gotta deliver. Nickel cadmium batteries are, in my opinion, wonderful things. We're all going to lithium ion batteries. And of course, lithium ion batteries are a whole lot better in terms of performance, but nickel cadmium batteries don't explode. I had students who had just got their eye surgery to go pilot, trying to pry off a lithium ion battery with a screwdriver, punctured it, and he was wearing safety goggles, so personal safety equipment, a must. So he's fine, but lots of paperwork, right? Nickel cadmium batteries don't explode. Make sure you do your power budget analysis well. And if you're not doing a heavy power stuff for your mission, and if you don't need all of the capacity for the lithium ion batteries, nickel cadmium batteries work great. Half our satellites are flying with nickel cadmium batteries and 0 problems, and less paperwork for me because students can't kill this as easily. LEDs all over the place. So why do you need LEDs on satellites that's going to go into space? You don't. But the mission success gets determined by the people who are working on the satellites on the ground. So if there's any kind of visual aids that can help you to do your development and design and work better on the satellite, it's going to help you be successful on orbit. Give you an example, we had a satellite, typical satellite, just you can't really see what's going on from the outside. A student was working on it, went to the bathroom for a couple of minutes. Another student came in to work on it, didn't realize the satellite was turned on, started working on it, and then all the single shot deploy mechanism popped open. That was another full week of reassembly and lots of pain. If there was a single LED that lit red to tell you that it was powered on, none of that would have happened, right? So a lot of visual cues. I'm a huge proponent. Big remover for flight pins everywhere. Highly recommend that because it's, again, people who are working on the satellite on the ground that needs to make this happen. Another thing I like for the students to take away from all this is to be a good engineer, I want you to get a good feel for what a good operating satellite does and sounds like. A good example is communications. So these days, everything can be automated. You just kind of sit at the ground station, push a button, and then make sure all the indicators are green. And if it's good, then you kind of sit there and move on. I really like having my first iteration of students making ground contact to do all the finger by hand contact. So they're sitting there sweating, trying to tune in for the Doppler shift, and they're doing the as-L control, trying to aim their antenna as the satellite's going overhead really fast. And they get to hear the tones, the Doppler shift, what a good data packet sounds like versus what a missed data packet sounds like. And getting that kind of feel, I think, is a huge value to the students, and especially if you go out in the field and start dealing with stuff that you're not familiar with. Having that kind of engineering sense, I think, is a valuable thing to have. So those are some of the experiences I wanted to share with you. Again, I'm very happy to be here. I think it's a great conference. Everyone is driving towards student education. So yeah. If you have any questions, I'll be here throughout the breaks, so please come see me. And yeah, thank you for your attention.
Thank you, Dr. King. So next up, we have a great presentation by NearSpace Launch. And you may have seen they have a really nice booth outside or in the next room. Let's see. And it's my pleasure to introduce one of the young and high-speed engineers at NearSpace Launch, John Pugsley.
Hello, everyone. So I am a recent graduate of college, undergrad. I started with NearSpace Launch back like 6 years ago, though I started in high school. So getting started early and kind of being able to continue working on satellites throughout college, and then kind of coming straight out of college and jumping right into a job, working on this stuff in the real world. It's all stuff you can do, and starting early is great. So to the students in the room, it's awesome. Keep doing it. And to the teachers, an encouragement that, when you can introduce students to cool stuff and encourage them to pursue that, if it's something that they're gonna be interested in long term, it's really cool to start early. So I'm gonna talk a little bit today about the ThinSats, which is kind of one of the ways that we've made satellites smaller and therefore more cost effective. So obviously cost is a huge barrier to entry for getting into space. A high altitude balloon, for example, is a much cheaper thing, or even maybe a sounding rocket is sometimes less expensive. But getting into space and actually doing all of that, not only is it complicated and you have to have a lot of resources at an engineering level, but you also have to have the money to be able to do it. So we're trying to make that cheaper. And there's been a couple ways that that's been happening over the last few years, and that's exciting to see. So I'm going to do a little bit of background about NSL. Some of you have already been stopping around our booth, and you may have heard Brandon's presentation yesterday, or his smaller presentation in the teachers' luncheon. But so NSL itself is the kind of main for-profit company, and then we started a nonprofit recently, NearSpace Education, and so there's kind of both of those tracks going on right now. But the commercial side started back in 2014 in Upland, Indiana. Started with a couple of guys who were kind of involved in university and industry, and were interested in getting a university to fly in space. And so they have 70 plus combined years in space science and engineering work. And it really started off with partnerships with universities. And so they basically wanted to get Indiana's first satellite off the ground with Taylor University. And they did that back in 2014 with kind of developing the bulk of the satellite on their own. And then Taylor was able to kind of, put in the student effort to build payload and work on parts of it. Some teams have the resources to build the entire satellite, and that's awesome. But often we've been helping universities who, maybe could do part of it, or you want to have a 2-semester project rather than a 5-year project. So we'll do most of it. We'll do the frame and the solar panels and the batteries and comms and these other things, and then the university provides a payload. So a lot of different avenues there. But so we started off a lot with universities. We did a lot of high altitude balloon launches early on because you get a lot of really good data that way and good testing of systems. And obviously that's much easier to turn that around, do another test in the next week, whereas a satellite is a much bigger investment. And you want to have a lot of testing done before you get to that point. Our satellite builds have kind of been spaced throughout, and started on the university side, but now we're doing more commercial and government stuff as well. So, and then one of the things that NSL has kind of worked in is pioneering that the satellite to constellation communication pathway. So a typical communication pathway is you have antenna on the satellite that's talking straight down to a radar dish on the ground, or a set of radar dishes that are kind of spread across the world as a ground station network. But one of the things that we've been working on for a long time is communicating up with the Globalstar and Iridium networks that are up higher. We're actually talking up to their networks, and then that gets relayed around and then sent back down to the ground. And those are the satellite constellations that, if you're going backpacking in the wilderness and want to buy a satellite phone, those are usually the networks that are providing that data. And so we're taking those same radios that you'd put in a satellite phone and putting that in space. And so there's obviously additional work that needs to be done. You can't just take that device and fly it right away. But that's something we've been doing for a long time, and switching over recently to Iridium, and had really good success with that. So kind of a current state of NSL, we do kind of a split between government, commercial, and still do a lot of university partnerships and high school and middle school stuff as well. And we've kind of got a few different set of products. As I said, the Iridium radios, the iStar S4 is what we call them. Those are the ones that are talking up and then relayed around and back down. That's a really small form factor, and you don't need attitude control, and you don't need to be transmitting at certain times. It's a 24/7 link with less than like 15 seconds from the time that the satellite decides to send data that you've got it on your cell phone or whatever, seeing the data coming in. So that's pretty cool. We also do, we call it the fast bus CubeSats, but anywhere from a 12U down to a 1U of, however much of the satellite you don't want to build yourself, we can build, and you do the rest. So that's especially in universities and other school organizations, being able to pick which part they want to focus on and then have the rest of it be handled separately. The black box is something that we've developed to basically take someone who's already flying a satellite. If you want redundancy on that satellite, you want to have kind of mission assurance, know that it's going to work. It's a fully independent barnacle, essentially, that you stick on the outside of your satellite. It has its own radio, battery, comms that can talk, main satellite fail. But then the kind of the two main areas that we're in right now that are really good for the education side are the Troop launches and the ThinSats, which we'll be kind of talking about for the rest of this. Troop is a hosted payload option, and it's something that is basically gets bolted on to the to a ring on the rocket, and it stays there connected to that, and it doesn't get ejected. And we have 4 different payload spots on that. So it's the nice thing is that you don't have to worry about as a payload loading onto it. You don't have to worry about the the comms, the power, the bus. All that's provided. You just provide a payload, and the rest of it's gonna be taken care of. And then the ThinSats is something that we started back a few years ago. It's kind of back when I got initially started back in high school, and that was an way of trying to miniaturize and say, how can we make these, even a 1U can be still an incredible launch cost. So how do we make that smaller? How do we make it cheaper? This is some just NSL heritage over the years. We kind of have done a lot of different systems, a lot of different satellites. We have over 800 different systems and subsystems in orbit to this point, which is exciting. So the ThinSats themselves was kind of a brainstorming of Bob Twiggs, who you probably heard about yesterday a little bit with the pocket cubes, but he's also, he's been a real advocate for bringing CubeSats into existence in the first place. So he kind of had multiple ideas back a few years back with how do we miniaturize, how do we make things smaller and more cost effective. And so he, in partnership with one of our co-founders and some others, basically came up with this idea of let's take a 1U or a 2U or a 3U and let's slice it up into 1/7 of a U slices. And each one of those will be a fully independent satellite. But now your launch cost has gone down on a per satellite basis because each organization has one payload. And it's not, you're not going to be flying huge experiments, but you can actually get a ton of good data out of a few circuit boards that are stacked on the inside of these. So the ThinSats are kind of there on that's 3 different ThinSats kind of spread apart a little bit. So those would be pushed together in the actual launch tube. And then you have each one is fully independent. So it's got its own radio that's talking down to the ground, its own battery, etc. And then you have the option to have extra solar fold-outs for more power. So obviously there's not very much surface area there to get very much solar. So doing a kind of a couple fold-outs between each one can increase power. The ThinSat program was something that was funded and kind of organized by Twig Space Labs and Virginia Space. And this was a couple years ago, kind of a pilot program for what's the feasibility of doing this with middle schools and high schools and maybe some universities. And so we had 60 of these launched in April of 2019 and 30 launched in 2021. And those were universities, a lot in Virginia and kind of other places across the Midwest. And it was a really good pilot program for what's the feasibility here? How do we, how can we make this something that a middle school or a high school can get involved, can make something and can fly it in a reasonable amount of time and in a reasonable cost. So the future for ThinSats, that program, the ThinSat program that Virginia Space ran with Twig Space Lab is kind of due to COVID especially and some other funding challenges isn't currently running, but the ThinSats themselves are something that we're continuing on both at the educational level and at the commercial level. One of the exciting things is that we're doing contracts right now with both NASA and the Air Force to use a slightly larger version of the ThinSats for commercial and government projects. And so the stuff that was piloted earlier is getting refined in this stage with government contracts and with NASA and the Air Force. And then we'll be able to bring that knowledge back into the education sector with the ThinSats at a middle school, high school, college level. And we're really excited to be able to do that here in the next few years of getting more schools that are interested in flying a satellite, maybe don't want to fly a full 1U, interested in this kind of how do we have a cheaper launch with still some really valuable data. So we're over in the main area. A lot of you have already come and talked to us, so definitely interested in talking more. That QR code has a thing you can just fill out a quick Google form and just say what you're interested more in, and we'll email you and follow up with flyers and more information as you're interested. But we also have a few different publications on the ThinSat program that were published at the SmallSat conference at different years. So there's some literature out there that you can pursue in more depth also. Thank you.
Thank you, John. We're going to take a 15-minute break, and please visit with the exhibitors, talk to the students, and we'll see you back at 10:50. Thank you.